Hello again. This is the last problem, I think, on your packet. Maybe not. Regardless, it's one of the hardest ones in your packet. There was a small missing word, and by small I mean actually quite large, inverted. So a water tank has the shape of an inverted right circular cone. These type of related rates problems are very common because they include geometric solids. You will always be given the formula for geometric solids volume or surface area if you need it on both my tests and the AP test. So that is not something you need to worry about rememorizing. But you do need to know what these solids look like. So what does a right circular cone look like? Well, it's a cone, and inverted means that the vertex, the pointy bit, is at the bottom. And I'm gonna come back to what, sorry about that. My pen bopped it. What the word right means here, because because they're giving it to us, that means it will be important later on. Let's just start filling in the other information we have. The radius at the base is 15 meters. The base is the flat part. 15 meters, and the height of the tank is 12. So we also have, that's also our height, 12. Water is flowing into the tank at a rate of 2 cubic meters per minute. So that means there's no water, then there's some water, then there's more water, then there's even more water, then there's more water. So water is increasing. So the first place where you might have gotten stuck, besides what does an inverted right circular cone look like, is what is this rate? 2 cubic meters per minute. And something that is gonna help you is looking at the units. Here we have, oh dear. Okay, here we have meters cubed. What is anything cubed tell us about? Usually volume. Volume per minute, that's a rate of volume. So that makes me think of dV with respect to time, since we're being measured meters cubed per minute. So we know that this is actually talking about the change in volume of the water in the tank. And as we can see, as water flows into the tank, it will take the shape of a cone. Now the cone itself doesn't look like the large gold cone always. It's gonna look like a smaller cone, a medium-sized cone, a slightly bigger cone, an even larger cone until the tank is full. What this means though is that we don't know what the height of the water cone is, or what's the radius. What's the radius here? What's the height here? But we do have this nice piece of information about the fact that it's a right circular cone. This means that if we take the height and the radius and the slant height of our cone, we get a right triangle. I'm gonna draw that out here. And this smaller water cone will also have a right triangle, where this is the water's radius and the height's radius. So this is the tank, and this is, the water. Sorry, you couldn't see that for a little bit. How is this going to help us? If we go back to the problem, we are asked to find how fast is the depth of the water in the tank increasing at the instant when the height of the water is 8. So we want H is going to equal 8. We still don't know what R will equal, and we want to find dH dt. This is what we want. Sorry, I will try to stop doing that. How are these two triangles going to help us with these 3 pieces of information? Well, here we have to go back to our triangle tools. These are right triangles. We could find the hypotenuse of this triangle, but that still wouldn't help us find the hypotenuse of this triangle. And really, we don't need slant height. So Pythagorean theorem is not a tool we want. Do we have any angles given to us? No. So trig is out. Inverse trig is out. What other triangle tools do we have? Reach into the depths of your geometry knowledge, and what I'm hoping you will access is similar triangles. From geometry, we know all right triangles are similar triangles because, not all, sorry. These triangles created will be similar triangles because they will have share this angle here. So by angle, similarity, these two triangles are similar. What I meant to say by all right triangles are similar is I meant to say all of the right triangles in this cone that will be formed by the water levels, the different water levels, will all be similar because of this angle similarity theorem. Since they are similar right triangles, we know that the corresponding sides are proportional, meaning radius over height is equal to radius over height. So we can do a couple of things. We're going to use this to help us in just a minute. We still need to come up with an equation that gets us dH dt, and maybe use this as well. So what this makes me think of is to use our volume formula for a cone, which is volume is equal to 1/3 pi r squared times height. We want dH dt. We have dV dt. This is a constant. R is also changing. Do we know what dr dt is? No. Can we find it? Maybe, but I don't really want to spend time doing that. I want to get to h, and what this nice equation here can help us with is we can rewrite r in terms of h. So let's simplify this to 5/4 is equal to r over h. Multiply both sides by h, we get 5h/4 equals r. Plug that in. V is equal to 1/3 pi 5h/4 squared times height. Now we have v in terms of h, and when we take the derivatives of both sides, we won't have to deal with r's at all. I hope this was helpful in getting you unstuck for this problem. This is a tricky one. We will talk about problems like this more frequently throughout the next week. Come to Flex, ask questions, write down questions you have. I have not finished the problem. I just want you to get started with what we have right here. I will see you either tomorrow or Monday. Enjoy the rest of your day. Have a good weekend if I don't see you tomorrow. Remember to get some sleep and do something fun. Goodbye.